So if I put this equation, the value of d here, then I will get the del dot or epsilon e is equal to rho v. Okay.
Yes.
Yes. And then of course I
Yes.
can write epsilon is a constant, so I can write del dot E is equal to rho v upon epsilon. This is also the form of Gauss law. This also we have discussed in this. Okay. Yes or no?
Yes, sir.
And here is the now comes the real scenario. E is equal to minus of gradient of V. This one I discussed in the last class. Do you remember?
Yes, sir.
Yes. Now you see, using the equation 3 and 4, can I write this equation 5?
Yes.
See very carefully. Using the 3 and 4, can I write this equation 5?
Yes.
Yes. Now this negative has been taken to this right hand side. Now see very carefully this part. This is, you see, this is something like divergence of gradient. This is something like divergence of gradient.
Gradient.
Yes. And if you see very carefully, if you can recall the definition, this is something like del upon del x x. So what will be the value of this? Do you think that this will, because this is divergence, this will be a scalar quantity, and this will be something like del square v. If you will solve this, you will get this again,
Okay.
del square v. Yes or no?
Yes.
So be very careful here, because this may be asked sometimes to match or sometimes. So del square v is equal to minus of rho v upon epsilon naught. So this equation, the final equation is known as Poisson's equation. This equation is known as Poisson's.
Poisson's equation.
So what is the Poisson's equation? And this operator del square is known as Laplacian operator. We have studied the gradient, divergence, and curl, and apart from that, there is another one that is known as the Laplacian operator. So this del square is the Laplacian operator, and this operator operates on both scalars and vector. So here it is operating on the scalar. So Laplacian of a scalar is divergence of gradient. This is what we have seen. So divergence of gradient.
Gradient.
Divergence of gradient. Del dot del f. So this is gradient, del f or del v. This is gradient. And here again, after taking the gradient, we are taking the divergence.
Okay.
Am I clear?
Yes, sir.
So this equation, del square v is equal to minus of v upon epsilon, is called as the Poisson's equation. Poisson's equation. Any doubt?
No, sir.
No. Now see, in this Poisson's equation, what is this rho v? In this Poisson's equation, what is this? Rho v,
Volume charge density.
volume charge density. So means, so suppose if there is a conductor, then by general plus 2 level theory, we know that, or you tell me what is the charge on the surface of a conductor. If there is a conductor, what is the charge on the surface of a conductor? What is the charge on the surface of a conductor? Hello?
Means
It is always zero. The charge on the surface of conductor is always zero. So if charge is zero, what is the value of rho v? If charge is zero, what is the value of rho v?
0.
Zero. So here, that is what in the previous slide it was written, that Laplace equation, what is what is the in the Laplace equation, in the Laplace equation, that is a special case of Poisson's equation. So Poisson's equation for a charge-free region. Listen very carefully this word. The Poisson's
Okay.
equation for a charge-free region, this side it becomes zero because charge-free means there is no charge. So no charge means rho v goes to zero. So that equation
Okay.
is called as the Laplace equation. So here is the equation, as you can see. This equation, del square v is equal to 0. So if it is equal to 0, then this is a special case. A special case means rho v is 0. So rho v is not always 0. Rho v is 0 for the certain special cases, like on the surface of a conductor, at the boundary interface. So that is why this is the special case of Poisson's equation.
Poison. Okay.
So
Okay.
any questions are clear to you? The Laplace equation and the Poisson's equation?
Yes, sir.
Yes. So this idea should be there that
Mm.
the meaning of the, then it is called as Laplace and then it is called as Poisson's. Okay.
Mm.
So just here, see the Laplace equation we can derive also, but here
Mm.
just directly it has been derived and the formula has been given for the all three coordinate system which we have studied. So as I told you that this expression is known as the Laplacian operator. Laplacian.
Mm. Mm.
Laplacian operator. So del square v is equal to divergence of gradient. This del square v
Mm.
is the divergence of gradient. So using this, we have already studied the gradient in Cartesian system. Already we have studied
Yes, sir.
gradient in the and the divergence in the Cartesian system. So if you apply
Yes.
in the Cartesian coordinate system, it will be del square v means second order partial derivative of v with respect to x plus second order partial derivative of v with respect to y plus second order partial derivative of v with respect to z. This is equal to 0.
Mm.
Okay. In the Cartesian
Ah.
coordinate system, in cylindrical, little bit changes will be there. As you can see, just we were having the formula there also for the gradient and divergence. So this will be 1 by rho times del y del rho of rho times del v upon del rho. So this you will have to remember from the book or from the slide presentation. This you will have to remember that the the Laplace equation in the cylindrical coordinate system is something like this, or you may derive if you remember this, the three things means delta of v, that means the gradient of v in the cylindrical coordinate system.
Mm.
If you know the formula of divergence of v, this we have discussed. Okay.
Yes, sir.
If
Mm.
you know the formula of divergence in the Cartesian coordinate system, sorry, cylindrical coordinate system, then the formula is here divergence of gradient. So this
Mm.
first v is a scalar. If you take its gradient, this will be a vector, and again if you take its divergence, then finally it will be a scalar.
Scalar.
Yes.
Mm.
If you know these three things, that Laplacian is divergence of gradient, then you may derive also. It is up to you. But if you remember, that will save
Yes,
you
sir.
time. So
Yes, sir.
Laplace equation in the cylindrical coordinate system is given like this. Quite clear?
Okay. Yes, sir.
Similarly, for the spherical coordinate system, this is the formula which you may derive or which you may remember. The choice is up to you. But if in examination it is asked, then you will have to choose or you will sorry, you have to do it
Mm.
correctly. So it is something like this. Formula is like this. Okay. So this is
Yes, sir.
the Laplace equation in all three coordinate system. This has been given in
Mm.
three coordinate system. Okay.
Yes, sir.
So here I don't think any doubt should be there because here it is just you have to understand the basics and then you will have to remember the formula. Okay.
Mm.
So shall we proceed? Okay. So application, okay. As I said, that potential at any point in between the two surface, when potential at the two surfaces are given, then it is mainly useful. If you have to find the potential between the two surfaces, and the known thing is that potential at the two surface. Okay.
Mm.
Also, this can be used to find the capacitance. Yes. How you can find the capacitance? See, as you are having the equation or something of the form del square V is equal to 0. Suppose you write the equation, then you integrate it one time, then you will get del V, means you will get something like this, del Vx, because three component will be there, del Vy and del Vz. Let me just illustrate you. Then final you can find the V as del Vx plus del Vy plus del Vz. Okay. And then
Mm.
again you will find, sorry, del V. Again, if you integrate, you will find V. And you know that there is a relation between C and V, that Q is equal to CV, so C is equal to Q upon V. Yes or no?
Yes.
Yes. So once you know the V between the two surfaces, then you can easily compute the value of capacitance between those two surfaces. Just you have to divide this by the Q. I mean, sorry, you have to just divide the Q by the V which you have computed.
Okay.
Did you get the point?
Yes, sir.
You don't need to go into much of the details. Means very complicated problem will not be there. Some small problems you may see here. As V is given, you see some function V is given. Epsilon is epsilon naught, means this is for the air or vacuum. Then there
Mm.
is a point given 1 3 minus 1. Then it is asking that find the V at the point P. Okay, and
Mm.
find V satisfies the Laplace equation. Just you have to check whether the V is satisfying the Laplace equation. So two parts. First, very quickly I will cover. V is equal to this much is given. So potential at this point, it is very simple. Just you put the coordinates here. You will get this as a minus 18 volt. Any problem?
No, sir.
No. Then you have to check whether it satisfies the Laplace equation. So Laplace equation in the Cartesian form is given like this: del square V upon del x square plus del square V upon del y square plus del square V upon del z square is equal to 0. Yes.
Yes. Yes.
Now you have to first differentiate the V. So if you
Mm.
differentiate this with respect to x, so what will be the value? Can you tell me?
2y cube z square. 2y cube z cube.
2y cube,
Z cube.
2y square z cube,
With respect to
x.
x. Uh, then
Rest all will be constant and differentiation of x is 1. So it will be 2y square.
yes.
So 2y square z cube.
In question it's y cube.
Sorry?
Uh,
Okay, okay. Here it is y cube. Okay, so then it will be 2
uh,
y cube z cube. Sorry.
uh,
2 y cube z cube. Sorry. Right.
Z cube.
Right here. It is 2y. Then what will be its second derivative with respect to x?
Mm, 0.
0. So see, the first thing which we are getting is del square v upon del x square is equal to 0. Similarly,
0.
you differentiate two times with respect to y and tell me what is the value of del square v upon del y square.
Mm. First it will come 2x 3y square z cube.
Hmm.
Then again 6x 2y z cube. 12xy z cube.
Okay, so means that is not 0. Okay,
Uh,
and similarly you check for the this one, means del square v upon del z square.
2xy cube 3z square. 12xy cube z.
Thing is that it is not 0. So if I put these three values here, then okay, first one was 0, okay, fine, but rest two are not 0. So 0 plus anything, and again, and both are positive. So 0 plus positive will not equal to 0. So means this does not satisfy the Laplace equation.
Laplace equation.
Am I clear?
Yes. Yes, sir.
No doubt in this question?
No.
So again, you may go through the some more. Here is the only difference is that it is in the spherical coordinate system. It is saying that consider the two concentric sphere of the radii A and B, where A is less than B. The outer means B is the outer sphere. The outer sphere is kept at a potential of V naught, and the inner sphere is at the zero potential. Solve the Laplace equation in the spherical coordinate to find the potential and electric field in the region between the two spheres. So just very quickly see the solution first. Later on you try some more questions by your own. See, see how to tackle this type of the problem. So from the given data, it is very obvious that V is a function of R only. Why I am saying that, or why the solution is saying that V is a function of R? Because you see here in the statement, if you see the statement of the question, it is saying that the two concentric sphere and they are kept at a constant potential V naught and the inner sphere at the zero potential. So of course means it is not a function of theta and phi, as the r will change because V is a function of r. We know that the V is equal to k q upon r, right?
Yes.
So V is a function of r. So what obvious is that del V upon del theta is 0 and del V upon del phi is also 0. Okay.
Zero.
So once we are equipped with this data, the del V upon this is 0. So the general expression is this one. This I told you, you will later on you will have to remember. But now I think that del V upon del theta is 0. So this term will straightway go to 0. Of course,
Yes.
del V upon del phi is 0. So this term will go to 0. Here again del V upon del theta is 0. So this term goes to 0 and 0 multiplied by anything is 0. So this entire term will go to 0.
Okay.
Yes or no?
Yes, sir.
So now I am left with only this much. Okay. So now, as I am left with this much, so see, according to the Laplace equation, del square V is equal to this and this is equal to 0 because Laplace equation says that del square V is 0. Yes.
Yes, sir.
So again, now if this is 0, so r square will multiply this side and I am left with finally this much of the only equation. Yes.
Yes. Yes.
Now you integrate, see del by del square. So if you integrate both sides, so you will get this side it is 0. So 0 times dx is 0, but you will be left with one integration constant.
Constant.
And del by del r will vanish. And now you will be left with r square times del
R
v
square del
equal to a. I hope.
A.
And now I can divide the r square this side and again I can go on integration for one more time with respect to r. Yes.
Yes.
So this del v will become b, and here again 1 by r square integration will be r to the power minus 2. So minus 2 plus 1, so minus of 1 upon r. Yes.
Yes.
So a upon r and plus another constant b. Okay. So we have calculated the. Am I clear?
Yes, sir.
But this V is now to be substituted with a boundary condition. This is what is the meaning of the boundary condition. So see just this example, and this will make some more things clear now. So what is the boundary condition is that it is saying that V is equal to V naught. The question is saying this is the meaning of boundary condition. At the boundary R is equal to B, and it said that for the inner circle the electrostatic potential was 0. So V is equal to 0 at A. Okay.
Yes.
So we have substituted that boundary condition and we will get an equation like this. V naught is equal to minus of A by B plus B. Okay. So then finally we will see. Then question I ask you, why we are putting the boundary condition? What is the need of the boundary condition? Why we are substituting the boundary condition? Tell me. We have studied the calculus. Why we are putting the boundary condition here? What is the need? Why we have already found the V, then why should I put the boundary condition? Tell me. See very carefully. I think you are here. We have found the B, but that is in terms of A and B. What are the A and B?
Yes. Okay. Some
What are A and B?
constant.
Constant. So if you can remember,
Mm-hmm.
the definite integral, lower limit, upper limit. Generally, we put
Mm.
the lower limit and upper limit to find the value of constant in the differential equation. Yes or no?
Mm. Yes.
Yes. So that is why these are unknowns. I need to know
Mm.
my constant A and B.
Mm. Mm.
To evaluate the constant, I will take help of the boundary condition.
Boundary condition. Mm.
Okay. So that is how the help has been taken. And then finally we found that A is equal to this something like this and B is equal to something like this. Let me show you.
Okay.
Yes. So something like this. This A is equal to something after solving and B is of course
Mm.
like this. Then
Mm.
you will get your final, then you will get your final expression of V like this. Then you will get your final expression of V as here. And the electric field, what is the relation between the electric field and V? Yesterday I have told you, yesterday means in the last class, I have told you what is the relation between E and V?
E vector equal to minus del V.
Grad of V. Once you
Grade.
know
Yeah.
the E,
Mm.
you can find the grad. If you remember the formula, so you can find the E. So
Okay.
this is how the Laplace and the Poisson's equation are useful while solving the boundary value problem. This is the one example of the boundary
Okay.
problem. So in
Okay.
while solving the Laplace equation, you will have to integrate two times.
Okay.
And then you will have to evaluate your constants using the boundary value
Boundary
condition.
condition. Mm.
Then if
Mm.
question asks that find the electric field, then you can take its gradient and put a negative sign. Don't forget to put the negative sign, otherwise it will go wrong. The answer will go wrong.
Mm.
So you take the gradient and put a negative sign there, then it will become the electric
Electric field. Okay.
field.
Yes, sir.
So this was perhaps the maximum about the means charge at rest. And now we will take very quickly and little bit. I will go little bit fast for the current. Means I will discuss the only the required things there about the current.
Okay.
Current. See, actually till now we have discussed that charge was at rest, right?
Mm.
But charge will not always be remain at the rest. It will move. And when the charge will move, when charge will move,
When there's a potential difference.
yes, so that potential we have studied, that electric field
Mm.
EMF we have studied. So once we
Mm.
apply that, now the charge will not remain at rest. So if it will
Mm.
not remain at rest, then what will happen? It will start moving.
Move. Mm.
The rate of flow of charge is called as
Current.
current. So and denoted by I.
I. Mm.
This current flows in the circuit or this flows over a surface. So generally this current we don't deal with the current directly. So we define the one more term that is called as current density. What is the current density?
Current per unit area.
Yes, and this is denoted by J. I is
Mm.
equal to J upon A. This current
Mm.
density is a vector quantity. Here again you need to be very careful. Current is a scalar quantity, but current density is a vector quantity.
Vector quantity.
What is
Mm.
the relation between J and I? J is, if it is a continuous current, then J is the integral of I dot ds or I dot A, I dot dA
Mm.
or I dot ds. So
A.
J, that is current density, is the I dot ds, where ds is the vector, I is a scalar, but finally this quantity is a vector. So current is
mm,
called as the current density, and this current density is the use of this, or the benefit of defining the current density, that current density can be defined at particular point, but current you cannot define at a point. Current will be either
mm,
flowing through a wire or through a surface. Okay,
mm,
but
mm,
current density you can define at point. If you go into its derivation, I'm not going here, then you will actually realize what is the significance of current density. So just at least
mm,
remember the significance. The significance of the current density is that it is applicable for points in a surface.
mm.
Am I clear?
Yes, sir.
Yes. And what is the relation? The relation is J is equal to integral, the surface integral of I over ds, the normal surface area.
Mm.
Yes?
Yes, sir.
So as you can see here, this is the I is equal to I out is equal to integral, the closed integral J dot ds. This up till here. Forget about that right hand side part. I will discuss about that. First, understand from here that I out is equal to J dot ds. Yes?
Mm.
Now, see, we are considering a case. We are considering a case, and what is the case? That suppose, see, suppose I am drawing a closed surface here, and charges are here. Suppose I am moving the charge from this surface outside like this. Okay.
Mm.
So if the charges are coming out of this surface, means charges are diminishing inside this surface.
Uh,
Yes or no? Diminishing means they are decreasing in this surface.
uh,
Yes or no?
yes.
If somebody is bringing the charges out of the surface, means charge is decreasing inside the surface.
Yes.
Yes. So this charge which is coming out of the surface, it will constitute current.
Yes.
So this is decreasing in the surface, means for this surface, this current will be minus of d by dt. D by dt means rate of flow of charge, because charge is coming out and hence it is decreasing. Wait. Hello? Huh? Good evening, Rishabh. Bolo. Okay, okay. Take it. Take it. Take it. Hello?